All right, what we're going to do is we're going to review some properties of cyclic groups, all sorts of different things we can do with them, and we'll focus on the cyclic group Z45 to begin with and look at some generalizations of that. Okay, so just remember that Z45, we can think about this as going from 0 to 1 to 2 to 3 and 4 and 5 and so on all the way around, and I've just labeled a few of them so that we can see them as we go here. So there's 25, 30, 35, 40, and of course 45 is 0 again. Okay, so the first thing we're going to do is we're going to find the subgroups of Z45. And so for the thing about a cyclic group is any subgroup is also cyclic. So one of the cyclic subgroups we can get is, of course, the group itself, which is generated by the number 1. So 1, 2, 3, 4, and so on. Because if you take 1 plus 1, you get 2. 1 plus 2, you get 3, and so on. It turns out that every divisor of 45, and in general, if you're looking in Zn, every divisor of n will give you a new cyclic subgroup. Okay, so 45 has a factor of 3, so the cyclic subgroup generated by 3 would be one of the cyclic subgroups. The next largest factor, 4, is not a factor, but 5 is. So the cyclic subgroup generated by 5 would be a subgroup of Z45. Next largest, let's see, 6 is not a divisor, 7, 8, 9. 9 is a divisor. And so if we do 9, and now let's just stop for a minute and remind you of what we mean by the cyclic subgroup generated by 9. So I'm going to do this with this because it's rather easy to list out the elements. Of course, because it's a subgroup, it has to have the identity. And then what I do is I just start listing the next largest number that I get by adding 9 to the previous number. So 0 plus 9 would give me 9. 9 plus 9 would give me 18. 18 plus 9 would give me 27. 27 plus 9 would give me 36. And then that is the last element in that cyclic subgroup. Observe that the order of the cyclic subgroup generated by 9 is 5. Also note that 45 divided by 9 is 5. What that means is if I want a cyclic subgroup of order 5, that is, that has 5 elements in it, I need to divide 45 by 5 to find out what element generates that. Okay, if we keep going, the next largest multiple or divisor of 45 would be, I guess, what, 15? Okay, and then the next largest divisor of 45 would be 45 itself, which we don't write. Actually, we would write the cyclic subgroup generated by 0, which, yes, it is a subgroup. It's a boring subgroup. It's the subgroup containing just the number 0. So the subgroups of Z45, there are 6 of them, each corresponding to one of the divisors of 45. Well, now we want to ask the question, what are the generators for Z45? Okay, so I'm not going to number all of these again, but I'll put a few of them on there. 0, 5, 10, 15, 20, 25, 30, 35, and 40. And we could ask the question, does 10 generate, yes, that's what that spells, Z45. Okay, so what we could do is we could start off with 0, and we could add 10 to 0, and that would get us to 10. And then if we add 10 to 10, we would get 20. If we add 10 to 20, we would get 30. Adding 10, we would get 40. And then if I add 10 to 40, I would get 50, but because we're in Z45, that would actually be 5, right? 50 mod 45 is 5. And if I keep adding 10, I'll get 15, add 10, I get 25, add 10, I get 35, add 10, I get 45, which is 0 again. Now the question is, does 10 generate it? And the answer is no. The reason it doesn't generate it is because we never obtained any number other than a multiple of 5. Now, one of the things we've talked about is that the generators of Z45 are the numbers that are relatively prime to 45, which are going to take me a while to list out, but let's see if we can do this. 1 and 2 Now, here's a little fact we learned. When certain numbers are generators, their additive inverse is also a generator. Okay, remember the additive inverse of 1 is the number we add to 1 to get 0. So that would be 45, or 44, I'm sorry, 45 minus 1. 45 minus 2 would give us 43. It's going to help me efficiently list these. 3 has a common factor with 45, so it does not generate it. But 4 would, which means 41 would. 5 has a common divisor. 6 has a common divisor. 7 does not, so 7 gets on my list, which means, now I have to be 38, and 8 would also be on the list, which means we get 37. 9, of course, is not. 10 has a common factor of 5, but 11 would be on the list, which means we get 34. And then 12, no, because a common factor of 3. 13, yes, which means 32. Let's see, 14, yeah, 14 works, which means we get 31. 15, not a chance. 16, yes, so we'd have 29. 17, it says 29 there. Let's just start all over there. 17 would work, so we get 28. 18 has a common factor of 3, so no. 19, yes, which means we would have, before 28, we'd have, what, 26? 20 has a common factor of 5, so it doesn't get included. 21 has a factor of 3. 22 would work. And that leaves us with 23 down here, and so those are all the generators of Z45. Okay, now we ask the question, what are the generators for the cyclic subgroup generated by 5? So once again, I've put the multiples of 5 on here. Certainly 5 will generate the cyclic subgroup generated by 5. That's a given. Now what I want to propose here is that let's not think about these as 0, 5, 10, 15, 20, 25, 30, and so on. Let's think about these as 0, and 5 is the first number in our cyclic subgroup, right? And 10 is the second number, even though I mislabeled it. That 10 should be actually over here. And 15 is 3, and so on. Okay, so we filled those in. So really, if I look at the inner circle, I'm looking at I'm looking at 0, 1, 2, 3, 4, 5, 6, 7, and 8, which really resembles Z9, does it not? And so we ask ourselves, hey, well, what generates Z9? What generates Z9? Well, once again, it's the elements that are relatively prime to 9. Okay, so what generates Z9s? The numbers that are relatively prime to 9 are 1, 2, but not 3, 4, 5, but not 6, 7, and 8. Okay, so what we can do is we can go around this wheel and say, well, 1 is 5, 2 is 10, we don't do 3, 4 is 20, 5 is 25, 6 we don't do, 7 is 35, and 8 is 40. So the numbers that would be generators for the cyclic subgroup generated by 5 are 5, 10, not 15, but 20, 25, 35, and 40. Okay, so those are the generators for the cyclic subgroup generated by 5. Now you might ask, why did some of these other ones not get the same consideration? Well, look at 30. What is the cyclic subgroup generated by 30? If it was a generator for the cyclic subgroup generated by 5, when I looked at multiples of 30, I should end up getting this exact same set, 0, 5, 10, 15, and so forth. Well, the cyclic subgroup generated by 30, I could start off with 0, and then I add 30 to that, I would get 30. Add 30 to that, I would get 60, which in mod 45, 60 is 15. And then if I add 30 to 15, I would get 45, which gets us back to 0. So you can see that this is not the same as the cyclic subgroup generated by 5. So here's the punchline for this. What did we do? We looked at the order of the cyclic subgroup generated by 5. There were 9 elements in there. Okay, and it's cyclic, so we thought of it like Z9. we looked at the generators of Z9 and then just looked at the multiples of 5, or 5 times each of those generators. So 5 times 1, down here we got 5 times 1 was 5, 5 times 2 was 10, 5 times 4 was 20, 5 times 5 is 25, 5 times 7 is 35, and 5 times 8 is 40. Okay, once again, we want to reflect on what's the relationship between 9 and 5. Well, because it was the cyclic subgroup generated by 5, and we're in Z45, if I take 45 divided by 5, I get 9. So that's the relationship between those two numbers. Another way I could have phrased this question is, what are the generators for the cyclic subgroup of order 9 in Z45? And that's what we're going to do next. Okay, so let's just think about this. What are the generators for the subgroup of Z45 of order 15? Okay, well, if it's of order 15, what I want to do is I want to take 45 and divide it by 15, which gives us 3. So the cyclic subgroup of order 15 in Z45 is the cyclic subgroup generated by 3. Okay, so this means that the order of 3 is 15. Okay, now let's try to put into practice what we just learned there. Let's think in Z15. What are the generators? We want numbers that are relatively prime to 15, so it would include 1 and 2, but it would not include 3. It would include 4, but not 5, not 6 even, but 7 and 8. 9 has a common factor of 3, 10 has a common factor of 5, but 11, 12 has a common factor of 3, 13, and 14. Okay, so again, this is in a cyclic subgroup of order 15. Those are the generators. What we need to do is we need to scale these by a factor of 3. So what I've done here is I've added the elements of the cyclic subgroup generated by 3, and now I'm going to add the corresponding sort of inner circle of these elements, the first, second, fourth, and so on. And so I've done that, which tells me that the cyclic subgroup generated by 3 has these generators. So let me circle them first. Whoops. Not you, Mr. 18. There we go. So what we're going to do is we're going to take each of the elements that I've listed down here in the circle and multiply them by 3. So my answer, it's getting a little sloppy now, would be 3, 6, 3 times 4 is 12, 15, not 15, how did I miss that? No, I'm sorry, 21. 7 times 3 is 21. 8 times 3 is 24. 11 times 3 is 33. 39. And 42. These are the generators of the cyclic subgroup of order 15 in Z45. All right, now we're going to do something weird, and I'm going to tie this all back in just a moment. I'm going to introduce to you a new group, and it's called the circle group, and it's a set of points on the unit circle. So I've just drawn all these points. And so the question is, well, what do you do with 2 points on the circle? How do you get the next point? Okay, so let's just suppose that A is right there, and this I need to do well because I might mess this up, but B is that point. What would A plus B be? Well, what it is we're going to take the angle that A makes with the positive x-axis. We'll creatively call that alpha. We'll take the angle that beta makes with the positive x-axis, or B makes with the positive x-axis. We'll call that beta. And what we're going to do is we're going to add alpha and beta together to get the next angle for the sum of A and B. Let's see if I can do this well. So I think that would be what we would consider A plus B, approximately. Let me make this a little bigger here. So that would be alpha plus beta. Okay, so that's how we get the next point on the unit circle, or that's how we get 2 points. Now the creative thing here is that you can realize each of these, for example, as a complex number. So down here, I'm going to realize this. I'm going to make that like a 45-degree angle here. So that would be the point. Let's say I went out 1 over radical 2, and then I went down. Since I went down, we would say minus 1 over radical 2 times I. Now the great thing about this is this circle group has some interesting subgroups within it. So for example, you can take this point here up at the top, this point here, this point there, and that point there. And really we shouldn't call this A plus B, we should call it A times B. I should make that little distinction. Well, this point up here is the point I. Over here is -1. Here is -I, and here is 1. So we have a subgroup H of T by taking 1 and -1, since I wrote -1 first, we'll put that there, I and -I, and that would be a subgroup of this that's finite, whereas T itself is an infinite collection. So here's something interesting. If you look at this very point, this guy right there, that value A is precisely the cosine of 2 pi over 4 plus I times the sine of 2 pi over 45. I think I said 2 pi over 4 for the cosine, but the cosine of 2 pi over 45 plus I times the sine of 2 pi over 45. If I look at another point here, that point is what? 1, let's count these, 1, 2, 3, 4, 5, 6. So that point is A to the 6th. Okay, looking at another one, if I keep going 1, that would be 7, 8, 9, 10, 11, 12, 13. This point right here is A to the 13th. Okay, this point right there is A to the 13th. So it's kind of an interesting thing, because what we now have is we have that the cyclic subgroup generated by A has order 45, because once I reach 45, once I go around 45, there I am back at the origin. Okay? Well, back at the identity, 1 plus 0 times I. And so we can ask all these other wonderful questions that we asked before. For example, what are the subgroups of this particular subgroups of the cyclic subgroup generated by A? Well, we just translate it into this notation. Well, certainly we would have the cyclic subgroup generated by A. We would have the cyclic subgroup generated by A cubed. Any divisor of 45, because A has order 45, will do it. The cyclic subgroup generated by A to the 5th, the cyclic subgroup generated by A to the 9th, by A to the 15th, and by A to the 45th. But this is kind of nice, because remember that A to the 45th is just the number 1. Okay? We can do those other crazy things. For example, we can ask, hey, what are the generators for the cyclic subgroup generated by A to the 5th? Well, if we look back at what we did before, we said, well, wait a minute, A to the 5th, the order of that group is going to be 9. So like we did before, we're going to look at Z sub 9 and say, well, what are the generators for that? In Z9, the generators were 1, 2, not 3, but 4, and 5, but not 6. We had 7 and 8. Okay, so what we're going to do is we're going to raise A to the 5th to each of those powers. So we'd have A to the 5th to the 1st, which is A to the 5th, A to the 5th squared, or A to the 10th, as his friends call him. We could also then have A to the 5th to the 4th, which is A to the 20th, A to the 5th to the 5th, A to the 25th to the 7th, which is A to the 35th, and to the 8th, which is A to the 40th. Compare that with your answers when we looked at the cyclic subgroup generated by 5 in the group Z sub 45.